Hi, everyone. My name is David Trong. I would like to thank everyone for being here. I hope everyone is having a good day so far. Today, I'd like to present my research project called Fault Containment in Distributed System that I've been working on with my mentor, Dr. Dasgupta from Valdosta State University. Before we get started, there's two terminology I'd like to discuss today. The first is the fault containment, and the second is the fault gap. Fault containment is the system ability to continue operating in undisturbed despite the failure of one or more of its components. The fault gap is basically the interval after which the system is ready to handle the next single fault. Method for fault containment allows a system to limit the impact of manifest fault to some predefined system boundaries. Furthermore, a single fault can potentially contaminate a large part of a network, and they are more likely to occur than multiple failures. Therefore, the research goal of our studies is to obtain eventual recovery from multi-failures along with efficient recovery from all single failures. Fault containment with a small fault gap and a solution of fault containment with a random scheduler. The method that I use can be described as using a web-based software called Eclipse. Eclipse is an IDE, which is an integrated development environment. It helps, is a free application that facilitates to help store, edit, and run various codes. One of the first thing I did with Dr. Dasgupta was to create a random graph generator that can produce any graph. I will. With this graph generator, I can create different nodes with different neighbors. Think of it like a family tree that connect to each other depending on other neighbor nodes. Next, I created a random number set for each node and the neighbors. And I was able to create a random generator that implements the algorithm that you see before you. On my poster, I have the algorithm there. So let's discuss a little bit more about the algorithm. The objective of the algorithm is to achieve stabilization. With stabilization means that all of it turns one color and the network is stabilizing itself. And to represent this, we created like different nodes that with different colors. And in the code, the output will be true or false. True will be green and false will be orange. So let's talk about how the algorithm works. There's three ways, like I mentioned. The first is whatever node is selected, that is selected is the fault node, which means that it is the local leader in the list and automatically will turn true. So if it's the local leader, then it will turn true, and if in a perfect environment, all of them will turn green. But let's just say we have like multiple faults node. Then you move on to step 2 and step 3. Step 2 is that if one of the neighbor nodes is not equal to the fault node, which is has two different numbers, then it will increase by m. M is whatever numbers that we chosen, and if it's true, then it flips. Then it becomes the local leader. Step 3 suggests that if the neighbor node is less than or equal to the fault node, then the neighbor node will increase by I, and I is a number that we generate, and that will be unchanged. So this will go on until the fault node becomes the local leader and turns true, which is green, and then thus our job and then thus reach stabilization. Again, our job is to report the time within the fault gap. So right here, you can see the results we have on the top right-hand corner. So I have observed the trend in the average time of the selected node numbers, and it seems that it's in a linear, which was very interesting. Is keep rising. If you look between the spike in the first picture, figure 1, you see that there was some error, but overall, I run the test over 100 times in order to get an accurate results. And you can see that the trend is that it's keep rising. And figure 2 demonstrate the trend in the degrees of the selected node numbers. And you see that it too has a linear results as well. The conclusion is that our work, the fault gap is independent of the network size. This improved the scalability and increased the availability of the system since it becomes ready to tolerate the next single fault with the same efficiency as soon as the observable variables recovers, with the high probability that the error does not spread to the distance to neighbors or beyond. So our future work, the above algorithm is an extension of the po-bit solution 2 and 3. And po-bit solution you can see right there. This is why we introduce a second variables in X in our solution. You can see the po-bits. There are other fault containment algorithms of similar types, and in future we want to conduct simulation experiment for those as well. Just try out different algorithms and different simulations. We would like to explore the conclusion in different typology, like the ring, star, or tree. This research is supported by the Blazer Summer Research Institute at Valdosta State University. So I had a great time working on this. We ran into problems like overflowing, overbuffering, just so much data was collected. So it was hard for the application to run all of it. It was a little slower once we hit 200 nodes. So we did from 10 to 20, 30, 40, 50, 100, 150, all the way to 200. So we scale it as big as we wanted, and we run it a lot of times to get the accuracy. So I would like to thank Dr. Dasgupta, Valdosta State University. I'd like to thank every one of you for being here. Thank you all, and I hope you have a wonderful day. Goodbye.